Okay, so you guys have understood about the, base width modulation and punch through action, right? So quickly, I will give you the minority carrier distribution in BJT for all the modes, right? So let us say this is my like VEB, like emitter to base junction, and this is my VCB. So what will happen if both are positive, like positive, and this is negative, this is positive, this is negative. If both are positive, what will be there? This would be my saturation region. And if EB is negative and CB is positive, then it will be inverse active. And if both are negative, then this will be cut off. And if this is the case, this is, we have already studied active mode, right? Now, let's say this is my PN junction. So this is my P plus region, N and P. So this is my JE and this is my JC, correct? So what is going to happen? I mean, I will roughly draw like saturation region. So saturation region, what will happen? This is forward bias, so it will be active, like let's say, I mean, this is first active mode. Active mode was what we have just now seen. We had seen that in active mode, my carrier concentration distribution was like this, and this will be this, and this will be this. Okay, I'm not drawing the like depletion width at each points. If I draw the depletion width, it will be a little bit much better. So in saturation region, it will be exactly same. Like towards this side, it is same as it is because it is forward biased JE region. This is my forward biased region, and this is also forward biased. So what will happen? See, instead of going this guy to zero, like this is my JE junction, and this is my JC junction. So in the base region, the meiotic carrier concentration is going almost zero. But since this is also forward biased, so it will go down, but it won't go to zero. So it will go a little bit up only. Okay. And then from here, it will go down. So this will be my meiotic carrier towards this, and this will be okay. So this is how the carrier distribution of PNP in saturation mode. Coming back to,
So how did you get that curve for the N part?
see, in active mode, what was happening? The meiotic carrier concentration, there was a gradient which was because of this is reversed. See, this is forward biased and this is reversed bias, right? So reversed bias, my meiotic carrier concentration gradient is becoming all, meiotic carrier is becoming zero because it is getting fully recombined, like full recombination is happening for PN node, right? So that's why it is reaching to PN node place. Okay. Now here what is happening is this is also forward biased. So forward bias, what will happen? This is N, this is P. So forward bias means this is positive and this is negative. So what will happen? The majority carrier concentration will be actually, this magnetic, electrons will get attracted towards. So the, what do you say? Base width will not get depleted, like base width will be contracted only. So for that purpose, the gradient will reduce, like dou px by dou x will be smaller, Similarly, dou nx by dou x, it will be smaller or bigger based on here. See, our aim is to find out how my carrier is getting diffused inside the layer, like collector region, base region, or emitter region. So we have seen here how my carriers were getting diffused, but this is not majority carriers, this is minority carriers. So minority carrier, anyway, this is very small earlier, but because of forward bias, it has little bit of higher place. You see the third one, then you will understand much better. Inverse active mode was what? Let me draw very clearly first. Forward bias. So this is my P plus region, N region, and P region. Let's say this is my NE node. Okay. This is my PN node, right? And this is my NC node. Okay. Now what would happen? So since this region is reversed biased, right? So my magnetic carrier concentration at the junction should go to 0. So instead of going this high, what will happen is it will go low. So it will go to 0. Okay. This is what will happen. Now, this guy is forward biased. So since this is forward biased, you can see this is forward biased here. So forward biased, what will happen? It will go and diffuse inside. So it should go and go diffuse inside. Okay. So this is the case. Now, how my gradient should change in the base region? So in the base region, actually, it should actually catch from this side to this side. So if it is going to catch from here to here, so my carrier distribution will be something like this. Okay. So this will be actually a positive slope. Okay. This is J, this is JC. Cutoff mode, both are reverse biased, right? Now, what should happen here? Since it is cutoff mode, both are reverse biased. So the magnetic carrier concentration should go to 0. Now, what should happen? It will increase, but again it should go to 0. And then again it should go to equilibrium place. So this is what is happening here. Okay. This is actually very important curve. Questions are being asked from this. Like how magnetic carriers gets distributed. So what will happen? Let me give you an exact question here. You tell me by yourself. This is reversed biased, right? So let's say right now I have given VCB1, okay, and you have got this curve. Let's say VCB2 we are giving, and that VCB, it is more than VCB1. So what will happen? You will see that since VCB2 is more than VCB1, so my depletion width will go a little bit inside base, isn't it? I mean, it will get more depleted because of reverse biasing. And since it has reversed bias, it has gone much deeper. So my, what do you say? The carrier gradient will go much down because it has to go to 0. It has much down. So if you see the curve 1 and this curve 2, so the curve 2 has more slope than curve 1. I mean, the like vanishing, like vanishing of carriers in mode 2, like I mean VCB2 is much faster. You mean to say dou P by dou X is greater in second case compared to dou P1 by dou X in first case. And if this is higher, then you will see your current IE has increased. In the same manner, IC will increase. Right? So by actually changing the reverse bias voltage, you are changing the base width, and since base width is changing, it is not having enough time to recombine. It is immediately recombining. I mean, because the width is very small, that's why IC is increasing. Okay, so you are controlling by controlling your reverse bias voltage. Okay, this is another question that was asked. And they are asking what is the configuration, I mean, what is the carrier distribution curve for different modes of action, like cutoff mode or inverse active mode or saturation mode or active mode. Okay, to see a question, the question is for a narrow base means base width is very small. Okay, so you can see here, you can see this is my like JC junction, sorry, JE junction, and this is my JC junction, and these are like depletion widths and all has happened. Okay, so the excess minority carrier concentrations Ne for emitter, delta Pb for base, and Nc for collector normalized to equilibrium minority carrier concentration, Ne node, Pb node, and Nc node. So we have already seen that. That's why it is saying 0. Like maybe it is taking a like a normalized case. So now what he's saying is which one of the following biasing mode is the transistor operating in? Okay, whether it is active, saturation, inverse, or cutoff. So what happened? This has gone down. So definitely this is reversed bias. So this is like reversed bias, right? Now this has gone up. Okay, so this must be forward biased. So forward biased and reverse biased. What would be the case? JC junction is forward biased and the JE junction is reverse biased. So JE, this is reversed, and JC, it is forward. So with this, you will get inverse. So this is inverse active mode. Okay. So in BJT, there are two kinds of breakdowns. Okay. In BJT, I'll just tell you BJT, two types of breakdown. Number one, we have already studied, which was punch through. Punch through. So what was happening? Like base width was reducing because of reverse bias voltage applied at the collector junction, and which was increasing, and that's how it was trying to, like remove the base itself, and that's why like BJT operation is getting ceased. Similarly, number two is avalanche breakdown. So just you keep the name in memory, because see, I mean, like NB and NC, like base doping and collector doping, both are small. Okay, they are moderately small. Why? Because collector has to collect the carriers. That's why the dopings are actually smaller in collector, and emitter doping is quite high. So the breakdown that will happen is avalanche. No Jenner will happen. No Jenner breakdown. No Jenner breakdown. Because to have Jenner diode, to have Jenner breakdown to happen, my carrier concentration must be very high. Like doping must be very high. Okay, so that was the reason avalanche breakdown is happening. Okay. Now one more term is there, which is called as thermal runaway. Just make a note, because they are asking like whether avalanche breakdown is available in BJT or not, or Jenner breakdown is available in BJT or not. So you have to say no, because the NB and NC dopings are small, right? Now, how can we save our BJTs? Like, how can we, what do you say? I mean, there will be thermal energy, right? Suppose it is getting heated up, so it will get burnt up. What happens basically is the reverse saturation current I naught. This is highly sensitive to temperature, that you know, highly sensitive to temperature. And you guys know the collector current IC was alpha times IE plus ICO. So what will happen? This IC can be written as beta times IB plus 1 plus beta times ICO or ICBO, right? So this guy is actually your current IEO. Now, this is reverse saturation current because it was due to minority carriers, and this is very small current. Now, as temperature increases or decreases, this current will be dominating. Like this current will start increasing very high. So since this is dominating, IC will depend on the minority carrier currents, right? So this guy will be nullified. So that's why thermal runaway will happen, like my BJT will get destroyed, right? So what is happening? The process is like this. Temperature is increasing. In that term, my I node is increasing. The reverse saturation current is increasing. And in that case, the IC is increasing very highly. IC is increasing very highly. Okay. So that's why the device temperature will also increase. Since temperature is increasing, IC will increase. IC is increasing, device temperature itself starts increasing. And that's why you will see the BJT that are made is something like this.
So what is IEO?
IEO is combination of these two, 1 plus beta times ICBO. IEBO or IEO you can write.
IEBO, yeah, yes, sir. Yes, sir.
ICO as I have written ICBO, right? See, ICN, ICO or ICBO. All are same. Now, when they make BJTs, what they do is they will keep this, like plunges kind of. Okay. So this guy actually helps to mitigate the heat. Okay. So these flanges will, like reduce the heat. If you keep little bit, like metallic continuously, so they will not, like dissipate heat much faster. But if you keep in this manner, in chip manner, so they will like reduce the heat very fast. So what you have to do, like how to reduce this effect? So you can increase the collector surface area. Okay, if collector surface area will be increased, so electrons will have ample amount of like place to diffuse through. Okay, or otherwise you can have good heat conducting metal around the collector, which acts as a heat sink. These are called as heat sink. Okay, or otherwise you can also use fans. So you will see that whenever BJT is used for high current application or something, they keep a fan there. So that fan will be running and it will keep the BJT cooler. Okay. Okay, so this was all about BJT. Now we'll move to junction field effect transistor. Okay. So in junction field effect transistor, what happens is basically, let's say this is my junction field effect transistor. So one terminal is gate, this is your source, and this is your drain. This is actually bulk, but bulk is actually like connected with source later on. Okay, so this is also called as source itself. Okay, so bulk is not like mentioned anywhere these days. And let's say this is your N type. So this is called substrate, and this guy is actually called as SiO2, silicon oxide layer, which is non-conductor. So if it is non-conducting, you will see my gate terminal is separated from the substrate by a oxide layer which is non-conducting. So the current entering to the gate terminal will not enter into the device. Okay. Got it? So basically, if I keep you, like 3D, you will have something like this. So this is actually the length which will be called as channel length, and this is suppose your N type material. Okay, this is also called as substrate, and this guy is your area of the device. So area depends on like what would be the like resistance of the channel or something like that. So what would be the resistance of this channel? R will be rho into L by A, right? So what is your aim? Your aim is to reduce the R, the resistance. So this resistance can be reduced by reducing the channel length. So if you reduce the channel length, what will happen? The source and drain will come very close to each other and there will be huge current conduction. Okay. So that to avoid, we cannot reduce the length. Now, if you try to reduce the, and sorry, try to increase the area, what will happen? R will reduce, but if you increase the area, what will happen? The device will be very, very bulky. So that also we don't want. My device should be miniaturized. I mean, it should be very small. Okay. So let us consider what is your source. So you can write down source. It is the terminal which supplies majority carriers into the device. Okay. So what will happen basically is from this guy, electrons will come and it will go to here. And that's why there will be a current, drain current ID. Okay. So you will see what is your drain current of the device. So ID. So since electrons are moving from source to drain, there will be a current which will be flowing from drain to source. Okay. So what is your drain? So drain, it is the terminal which receives majority carrier out of the device. So the source which was supplying the majority carrier, that will be received by the drain. And what is the gate? So gate is just like base in BJT. Base was controlling your like current from emitter to collector. The same manner, the gate will control the current from drain to source. Like gate is the controlling terminal. So it is the terminal which controls the current flow through the device. One more thing, you would have understood by now, the BJT was current control device. Why? Because the majority carriers were getting recombined in the base, and that's why my base current was reducing or increasing. And since the base current was reducing or increasing, based on that, my IC was getting controlled. Like IC was increasing or decreasing. So it was IB, the base current, which was controlling the device. That's why BJT is a current control device. Okay. Whereas I will show you how gate is going to control the drain to source current, and that's how gate voltage will be the like a parameter which will control the device. That's why MOSFET or like JFET is called as voltage control device. So we'll see that. Huh? You have seen how gate, base current was controlling that. Now we will see how gate voltage will control this, right? So let us take different cases and we'll try to understand what is the functionality. Please complete up to this. Okay. So let us say case 1, Vg is not 0 but a small. Okay, so what will happen? This is your source, this is your drain, and this was gate. So I am going to apply a voltage Vg positive, okay, and this is your bulb. So what will happen? Since voltage is applied, this is your N region, right? N type. So positive, what it will try to do? It will try to create a depletion width. So the channel will start getting reduced because depletion will start happening. Okay. So I am doing both the side because it is actually looking two-dimensional. That's why it is looking like this. But if it is happening to be, like 3D, you will see this, like this as a, what do you say? Both the side it will happen. So suppose this is your depletion that has happened. Now let us try to consider the total width was 2A and this width is 2A dash. So definitely you can say one more thing I am considering is there is no drain voltage applied or source voltage applied. So I can tell VDS is 0 and VG2S is varying. Okay, got it? So this is what is happening. Now if I try to increase VG more, then what will happen? This is source, this is drain, and this is your gate where you are applying VG. Okay, so in that case my depletion width will increase little further, right? So the channel which is available is much smaller. So this is 2A dash. So you can see A dash is a function of applied voltage VGS. Okay, like whatever the voltage B VG you are applying with respect to source, so VGS. Okay, so this is a function of VGS. So VGS is more, A dash will be less. Okay, so I will give you a terminology here. Ki the voltage VGS, okay, at which 2A dash is 0. 2A dash is equal to 0 is called as pinch off voltage. So you are seeing how my base, like depletion width was increasing because of applied voltage at gate, and it is going to seize the channel itself. And that's what is the place which is called as pinch off voltage. So you can see, let us say this is your N type channel. So total width was, let's say 2xn, and this is your 2A dash or 2A. So 2A dash, or you can say 2A minus 2xn, okay, is 0 at VGS is equal to VP, okay, like pinch of voltage. So you can say my xn, the, what is that? The depletion width, which is xn. So total width is 2xn, both the side. So if xn is equal to half A, like A, 2A was total channel width. So if it is A, where xn is the depletion width in N side, this was N type, so xn I have taken. So if xn it is 0 equal to, so xn is equal to A, then I will tell I have reached up to pinch of voltage. So at what voltage my channel ceases to exist is called as pinch of voltage. Okay. Please write down. One minute, boss. Okay. So now with our definitions that we have already studied, we can say this is anyway PN junction, right? So can you say here about the resistance of the channel? Resistance R was actually what? Rho into L by A. A we can consider it as, let's say, thickness into 2A dash, right? The width. So since 2A dash is keep on what is that? Decreasing, my resistance of the like device is increasing. That you can now consider, since overall area was reducing, right? And you guys know now how my charge distribution and electric field distribution and the voltage distribution will happen. So in that case, I'll just quickly draw this side. Let's say this is your xn and this is your xp. Okay. So this is your charge distribution rho v. Similarly, the electric field distribution will be what? Like this. This is your electric field. Okay. And what was voltage? This would be like this. This is your voltage, right? So if you can see, just now I told you, either it can be in two terms, like whether it can be like xn side or xp side. Suppose it is like p type, then it will be xp, or it will, if it is n type, then it will be xn. So what will happen? My electric field into the distance will be voltage. So the pinch of voltage Vp, what I have found, that I want to derive it from the theoretical calculation. That's what the question will be asking you. So what is the maximum electric field? So Q into Na into xp divided by epsilon, right? Into See, I have considered 2 times xn, so 2 times xp. So half of that will be 1 by 2 times xp must be equal to vp. Okay. So if this happens, then what will happen? Or otherwise, q times nd into xn divided by epsilon multiplied by 1 by 2 times xn must be vp or vn. The pinch of voltage in vn. So can you say from here my vn into 2 times epsilon, right? Or I will write it 2 vn times epsilon must be equal to or divided by q into nd, right? Q into nd must be equal to xn square, right? And since this xn was actually equal to a square once it becomes pinch voltage, right? So with that, you are going to get your vp or vn, right, is equal to what? Q times nd times a square by 2 epsilon. So the expressions for pinch of voltage you have got in terms of doping concentration and in terms of the device width. Okay, so device width, half width is A. Okay, total width is 2A.
So what's the difference between VP and VN?
Vn I have kept it for like N channel and Vp I have kept it for P channel, but both are, I mean, pinch of voltage only. You don't have to consider it separately. I mean, for both you can keep it Vp, but see, Vp will be greater than 0 for one type and Vp will be less than 0 for other type, right? For N channel, it will be more than 0. For P channel, it will be less than 0. I mean, negative voltage must be applied to create a depletion width for P type. For P type, how depletion width will increase? You have to apply negative voltage there, right? So that's why Vp will be less than 0 for P channel JFET, and this will be for N channel JFET. So basically, pinch of voltage, you can write a definition. I mean, I have anyway explained it. Is it done up to here?
So then how is xn square equal to a square?
See, xn. See, what was happening is, you see here, this is your total width of the device is 2A, right? Now, as width is decreasing, I have kept it 2A prime. Okay. Now, xn is the depletion width that has happened in N channel. So xn up and xn down also. So 2xn, right? Now this 2xn will become equal to 2A. Then only, see this, or 2xn I have written here. Total width is 2A.
Yes, sir. Yes.
Yeah. So if 2xn will be equal to 2A, then only my pinch of voltage, I mean, sorry, then only the channel will become 0. So
Yes.
that voltage applied will be Vp.
Yes.
Okay. Got it? So you can write down the pinch of voltage. It is the gate to source voltage at which channel ceases to exist. I mean, channel does not exist. Okay. So we have understood what is the, function when my gate voltage was changing. Okay. Now next case will be, what would be the change in the channel when my drain to source voltage is also changing. Okay. So what happens is, once my channel starts, we'll keep that voltage constant at VG, because VG is a controlling voltage. So VG we cannot, keep on changing. And main voltage is actually drain to source voltage. So drain to source voltage we will vary, and that's how my device will function. All right. So what we'll do is, we'll